All right, welcome to another exciting biomedical imaging class. What I'd like to do is emphasize some of the basics of image processing and just talk a little bit about what is image processing. And what I'll do here is, here we go. So, last time we had a chit-chat about what is image processing, and we defined image processing based on the fact that it is a kind of data processing. Data processing involving an image. So we input an image, we output an image, we call it image processing. That's simple enough, right? Image processing is kind of different from, let's say, computer graphics. And last time we talked about computer graphics, we talked about geometry. And when we talk about the difference between image processing and voice and signal processing, it's the difference between 1D processing and 2D processing. So when I think about signal processing, I think about a kind of data processing that involves what I would call vectors, where the vector is a one-dimensional array. And the vector processing architecture is called signal processing, and the kinds of chips that do the signal processing are called digital signal processing chips, or DSP chips. Those chips, generally speaking, have much higher bandwidth than, let's say, general-purpose CPUs that we're used to. For example, when you think about a large array with a single operation, we have a special, what they call Flynn taxonomy, that describes that processor. Has anybody ever heard of the Flynn taxonomy before? You would have to have a computer architecture class. Does anyone here have a computer architecture class? Yes? Does anybody remember anything in computer? No. So let me see if I can remind you a little bit about Flynn taxonomy. Right? We have SIMD and we have MIMD. SIMD, what's that stand for? Yeah. You've been brainwashed by Professor Line. Congratulations. Yes, signal, instruction, multiple data. Oh, wait. We don't call it brainwashing. We call it education. So now, if we know what SIMD is, single instruction, multiple data, what could MIMD stand for? Multiple instruction, multiple data. All right, that's great. So if I have a single instruction, multiple data, that's one operation that occurs over all of the data in the vector. That kind of single instruction, multiple data, that's called digital signal processing. It's a fancy way, SIMD is a fancy way of saying DSP. So when you think about voice and signal processing, think SIMD. Think DSP chips. And the DSP chips are really very good at processing homogeneous data. That means all the data is the same. So if you've got a big vector of a whole bunch of the same data, what good is that? Well, if you're dealing with streaming data, that's audio coming in off the web, that's SIMD type data, that's SIMD type operations, and it is one of those things where you would ultimately call it multimedia data processing. Right? Multimedia data processing means more than one kind of media. It can be one-dimensional arrays, two-dimensional arrays, three-dimensional arrays, which might refer to image sequences. Those are specialty architectures. So when we think about SIMD and DSP, we often think, gee, if I had a CPU that was very good at it, but also good at other things, we'd have a specialized instruction set for that CPU. So if you had Intel inside, you might actually have some SIMD instructions. What would you call, well, what does Intel call the SIMD instructions inside of an Intel processor? Any ideas? Yeah, MMX, multimedia extensions. So those are the SIMD instructions. They took those MMX instructions in the Pentium 3 and they extended them with SSE. What does that stand for? You guys have computers, right? Can't you just look this up? SSE and SSE2. Right? Don't you guys have Google? They have Google in here. Don't they have Google? You know how to Google things, right? You put it in the text field and you hit enter and the stuff comes out and you say, oh yeah, that's what it stands for. No? Yes, SIMD extensions. So it's really all about SIMD. So Flynn taxonomy is built in to the marketing of Intel chips because they come with SSE and SSE2 instructions, which means they are geared for signal processing. They're multimedia capable. And what did Intel discover when it started to market its chips with MMX and SSE and SSE2 instructions? It discovered that Joe Schmo on the street has no idea what they were talking about. They did an extraordinarily poor job of educating John Q. Public. Because John Q. Public goes into Walmart and buys a computer that's cheap. And John Q. Public doesn't care about SSE and MMX because John Q. Public doesn't know. But you, as computer engineering students, you know how important that is. A lot of good it does you because you can't remember. But you knew at one point how important it was. Somebody might say, gee, maybe it's just marketing. And yes, it's true. It is just marketing. But also, there is a technical difference, right? MMX, SSE, SSE2, these are important features for that CPU line. However, if you went to Motorola, which is now Freescale, and bought a PowerPC, you would find they actually started it with what's called the AltiVec, another marketing term, which is essentially MMX and SSE and SSE2. It's a vector processing unit, VPU they called it. And in that vector processing unit instructions, what did they do? Voice and signal processing. They did multimedia data processing or vector processing. So this is the kind of thing that impacts an entire industry because once AltiVec instructions or vector processing unit type instructions came out with the PowerPC, Intel said, I got to get me some of that. And so they put it in as well. And they weren't the first. Initially, it was the mainframe manufacturers, IBM and Cray, with their vector supercomputers that were trying to do the signal processing. They had what they called systolic or bag-on-the-side type array processors. And those systolic array processors were all for voice and signal processing. And then Gould came out with De Anza's, and De Anza's had image processing units built into the mini computers. This is all part of computer history, but all of these things came about so that eventually today we can get, well, essentially what is supercomputer type technology built into our laptops. Isn't that exciting? Not so exciting. Well, I feel badly for you because you're a computer engineer, and if you can't get excited about that, too bad. So, as it happens, if you think about computer graphics, there's another opportunity for specialized computer architecture. Right? What is computer graphics? Well, the input and output is different. Right? The input is geometry, the output is images. Oh, it says output. Output. Let's fix that. Output. Gotta fix my slides here. Excuse me. Didn't even notice that. Yeah. And so the output is images. Now, as it happens, there is a gray zone where you might say, gee, the geometry is on input, but it might be that I also have images that come in on input. And I can texture map those images around a sphere, right? So is that image processing? Kinda. A little bit. So there's some gray zone in all of that where you're mixing in geometry and images, but that's fine. So when I think about computer graphics, I definitely want to think about geometry at some level. And there's many kinds of geometry, right? There's constructive solid geometry, there's boundary representations, there's parametric forms, there's implicit forms, but let's just call it geometry. Now I think about computer vision. Believe it or not, it's a whole other field with a whole other area that you can study. And the input is still images, but the output now can be geometry or some symbolic representation. Like you take a picture of something and it says, aha, a terrorist. Or you take a picture of something and it says, aha, $5.25 is on the table, and counts the change. So symbolic output is a perfectly reasonable output. It doesn't have to be geometry. So if computer vision is images going into geometry and computer graphics is geometry going into images, one might make the claim that computer graphics is the dual of computer vision. But most people wouldn't necessarily agree with that. In some ways, one would say if you're doing pattern recognition with images, that's computer vision. If I did pattern recognition with sound, that's not computer vision, right? If I take text and convert it into speech, well, that's voice and signal processing. That's speech synthesis. But if I take speech and convert it into text, well, that's speech recognition. And it is a form of pattern recognition, but it's not computer vision because it's not dealing with images. So then comes the big questions, right? Sort of, what's an image? And you'd say, well, maybe it's a 2D array of pixels. Does it have to be visible? No. Where would I find invisible images? Well, in the biomedical imaging community, it's X-rays, MRIs. Maybe in the astronomy community, it's infrared. You could do infrared for biomedical imaging, as a matter of fact. You could have ultraviolet. Where else could I get images? Sure, I could have ultrasound, I could have CAT scan, any place you can have energy. How about microwaves? Radar systems. They give me images, right? Radar images are images. Where else can I get images? How about sonar from submarines? That's legit, right? Those are images. Where else can I get images? Well, okay, how about this? Where else can I find energy? Right? We talk about sound, that's a pressure wave. Fine. How about electromagnetics? I've got light, right? I've got what we call radio waves, so that's like the microwaves. I've got the X-rays. How about cosmic rays? Could I image cosmic radiation? Yeah, sure, why not? So in some sense, my imaging system, it could be anywhere. It could be ground-based, it could be space-based, right? I could have a satellite. Voyager, for example, has infrared astronomical scopes on it. Can't use them anymore because it's left the heliosphere, but in effect, it had infrared imaging systems on it. Everybody know what the heliosphere is? No? You ever heard of this heliosphere? That's where the sun's influence ceases. Pluto, which was a planet when I grew up, was influenced by the solar wind. It was within the heliosphere. But when you go beyond the heliosphere, then the sun no longer has any influence on you. And so the heliosphere is beyond Pluto. And they've turned the camera back on our solar system to take a picture of our solar system. And the Earth is less than 1 pixel in size in terms of the whole resolution of the image that you can get back. And it just lets us know how small we are relative to our solar system. So then the question becomes, what is a digital image? I used to work on Voyager, when I was at the Jet Propulsion Lab. It's running out of batteries as 2 years. Runs out of batteries. Well, batteries run down gradually. They're plutonium, you know. And plutonium has kind of a long half-life, but for some reason the batteries don't last as long as you might think based on plutonium's half-life. They're thermopiles, you know. So an image as an array has to be quantized. And when we think about digitization, we think about two things, right? We quantize in time and we quantize in value. When we quantize in time, we are said to sample, right? So take a continuous function and sample it in time, and that is essentially quantization in time, sampling. Take that continuous function and divide it up into a finite number of values, and that's quantization of the sample to, let's say, the nearest value. And when we think about sampling rates, we also think about Nyquist, right? Can somebody remember the Nyquist theorem for me? Yes, the sampling rate has to be twice the highest frequency that you intend to reconstruct, at a minimum. At a minimum. So then there are all these interesting and wonderful images that you can create, but when you create a computer display for humans, you want to stimulate the human visual system. And the human visual system has peaks at red, green, and blue because of the rods and cones that are in our retinas. And so when you create a light system for humans, if you want white light, you have to have equal quantities of red, green, and blue. And here we go. We'll take a little section of it and blow it up, and then blow that up, and then you can see values that come out from subsections inside of an image. And those values can range from, well, let's say any number to any other number. The question of what the dynamic range is depends on how many bits you have per pixel. Typically, a 24-bit image is called a direct color image. It gives you 8 bits for red, 8 bits for green, and 8 bits for blue. And that means you can have numbers that range from 0 to 255 for red, and numbers that range from 0 to 255 for green, and numbers that range from 0 to 255 for blue. And that's very typical. And then what you do is you take those numbers for red, green, and blue, and you load them up into some RAM that can be clocked out to a digital analog converter very quickly, and that is called a graphics card. Right? And the graphics card's got this RAM in it, and it can send out a signal to the red, green, and blue inputs on your display, and then you get to see your image. And that's what you call graphics card architecture. So in order to be able to access the RAM, what you do is you memory map all of that RAM into the CPU's memory space, and then you write out the data right from your computer program. And then you go and take that image buffer and you strobe the entire thing into your graphics card. And then it gets displayed. So you'll have 3 different values for each pixel. Which means if you need 1 million pixels, you need 1 million bytes for red, 1 million bytes for green, and 1 million bytes for blue. Right? For a 24-bit image, that means a 1 million pixel image, and that's not that big anymore, needs 3 megabytes of data. Now the question of whether or not you compress the data is another matter. Right? You could store the data compressed or uncompressed. If it's stored uncompressed, then you really do need 3 megabytes. And then the question is, how do you want to store 3 megabytes in your computer program as a programmer? Right? Well, maybe I could make 1 million bytes in an array of byte, and then I'll get another 1 million bytes in another array of byte, and another array of bytes. And now I could have, 3 megabytes with 3 byte arrays. But that might not be a very efficient way to go if I have a 32-bit computer. Right? Because the 32-bit computer wants to process 32 bits at a time. It has a 32-bit bus. It has a 32-bit CPU. It has 32-bit registers. So it's not a very efficient thing to have it, throw away everything but 8 bits. Right? It's just like, well, I care about the least significant 8 bits, and who cares about the most significant 24 bits? That's nonsense, right? You're going to be I/O bound. So what do you do as a programmer? Any ideas? To manipulate an entire pixel all at once, take the red, green, and blue pixels and pack them into a single 32-bit quantity. That way, when you retrieve a pixel, you can get all the colors for that pixel all at once. And for the 8 bits and the most significant part of the pixel, well, you can call that the alpha or overlay plane. So now when you're dealing with a 32-bit int, and every Java virtual machine is a 32-bit machine, you will be able to have an entire pixel, including an overlay plane, contained in that 32-bit quantity. That's really the most efficient way to handle it. Then you could say, oh, what happens if I have a 64-bit machine? Like, oh boy. Then you got to handle 2 pixels at a time. But that's not so bad, because you can do a little bit of a look ahead when you go to grab that stuff. Somebody asked, Brian, I think it was you, what about Intel's virtual cores? I looked into that. And virtual cores are a way in which Intel does speculative branching in order to simulate multiple cores and take advantage of a superscalar architecture. So it's a specialized way to execute multiple instructions in a single CPU cycle. And so that's what Intel was referring to when it talked about its new marketing term, the virtual cores. So you can get a quad-core system with 12 virtual cores in a, I think they're calling it an i7 now. I have no idea where they get these names, right? I really no idea. Does an i7, does that have 8 cores? Or does it have 4 cores? I really don't, why did they call it that? Yeah, why not just call it by the number of cores? Like I have this thing here, it's called the V Pro. And it's trademarked too. What's a V Pro? I got no idea. They really they missed the boat on that when they marketed to me, because I don't pay much attention to that stuff, but I should. I should, because it's interesting and we should know more about what's going on here. So when we take an image and we want to form it on the screen, we take our array, we strobe it to our RAM, we have the RAM display it to this digital to analog converter, and then our big question is, what will the image appear like? That's an interesting question, because that has to do with perception, right? The perceptual quantity that is seen by the, I'll call it eye-brain interface, is not one that can be easily understood, because it will look different to different people. Different people see things differently. That's a very interesting point. So the person who is red-green colorblind doesn't see the same colors you do. A snake doesn't see the same colors you do. They see into the infrared. Some animals might see into the ultraviolet. So everybody perceives the energy differently. If you were evolved on a different planet, let's say Mars, the red planet, you might not have an eye which is maximally sensitive to green. You might have an eye that's maximally sensitive to red, assuming you could live on Mars. There are Earth-like planets which have different underlying colors. And people have hypothesized what life might be like on those planets if those planets supported life, because they're evolving with different colors. Isn't that interesting? We can spend we can have a lot of fun hypothesizing on what life might be like on these other planets, Earth-like planets. The Kepler Space Telescope is designed to find Earth-like planets. That's its primary goal. It's part of the search for life. So there are these sort of interesting things that are going on in the world and in space that involve imaging. Right? Isn't that cool? let me see if I can get my, so here is quantization, right, in value. And if you look at the little dots and how they've been distributed along the x-axis, that's quantization in time, or for a two-dimensional image, it's spatial quantization. Spatial quantization refers to the number of dots per inch. Temporal quantization refers to the number of samples per second. We don't normally refer to temporal quantization in image processing except by the number of frames per second. So if you're doing image sequence processing, then you get temporal quantization. Right? So now let's think about that in terms of frames per second. Can somebody tell me how many frames per second do you normally get with video? What we normally call video here in this country. Yes, sir. Well, 24 frames per second would be film, but each image is shown twice. And as a result, it looks like there's 48 frames per second, but in fact there are really only 24 unique frames. For video, broadcast video, how many frames per second would you get for standard definition? 30 frames per second, but they have an odd field and an even field. That's interlace. And so the rate is 60 for the overall number of fields, but for the entire image you get 30 frames per second. But if you think in terms of HD TV, then 60 is a correct answer, especially when you're dealing with what they call progressive scan, which is not interlaced. And that's quite typical nowadays. I don't know if anybody knows, but there are now 3 major HD TV standards which are in use commonly today. One is called the 787 standard, the other is called the 1125 standard, and the other is called the 1050 standard. The 787 standard is the AT&T Zenith standard. I used to know this because I worked in the field. When I was at Bell Labs, I worked on image sequence synthesis for the FCC test images. This is prior to their settling on an HDTV standard. They didn't want to get sued, so they settled on all 3 standards. This is what happens when you design a system by committee. So now we've got a progressive system, the 787 system, and now we also have interlace systems, 1125 and 1050, which is unfortunate. The theory was that they would be manufacturing HDTV televisions in this country. Never happened, except maybe in prototype. The only thing they make in this country is the glass for the HDTVs. Corning makes the glass. That they make in this country. What a pity. So this is an interesting point. If you said to me, well, images that we know are 8 bits per color, what happens to image processing subroutine libraries that try to work with images that are not 8 bits per color? Where would you get an image that's not 8 bits per color? Any ideas?
On my computer?
Yeah? Well, I don't know. On your computer, Hubble Space Telescope will give 16 bits per color, but the color won't be red, green, and blue. So it might want to measure something like from the ultraviolet or the X-ray. And in fact, what you're dealing with is a very, I'll call it, high dynamic range sensor. So with high dynamic range sensors, with very good signal-to-noise ratio, you can get lots more than 8 bits worth of dynamic range. And to answer the question, your subroutine libraries may have to be modified, especially if you've customized them and optimized them for 8-bit images. And that's a big problem. So when you start to think about these assertions, oh yeah, an image is red, green, and blue. You're like, okay, what happens when it's not? Oh, an image is 8 bits per color. Okay, what happens when it's not? Are those assumptions valid? Well, the answer is they aren't necessarily valid, and you should question everything. So if you build this giant, humongous library like I've done around 8-bit images, and then find out, hey, wait a minute, I want to start doing Hubble Space Telescope images, it's a problem. So what happens if you don't want to settle on just 8 bits per color? What do you do? What if you don't know how many bits you're going to have per color? What if you want a general purpose image processing program that works with non-quantized images? Now R, G, and B have to be floats, right? If you have floating point numbers, you've got a lot more dynamic range. You could have 32 bits. But if you have 32 bits, right, that's 4 bytes. So that means 4 bytes for red, 4 bytes for green, 4 bytes for blue. That's 12 bytes in total per pixel. So take 12 and multiply by a 1 megapixel image. Now you need 12 megabytes for each image. That's a lot more data processing, a lot more data to move through your CPU in order to be able to do basic image processing operations. You will pay for that. Things will get slow, but you'll have this dynamic range. And here's the governor of California, I think. Isn't that him? That's Arnold, right? Isn't that Arnold Schwartz? I'm not sure. One thing we know is he was a very good Terminator. Maybe not such a great governor, but a very good Terminator. And now the question becomes, how do I know when image processing is computer graphics? Here the input is an image, but it looks to me like the output is a kind of a geometry, right? So is it computer vision, or is it computer graphics? Right? That's a big question. What we're getting here, what we're getting to at the bottom, the point here. What's the point? The point is, it's not clear. It's not clear whether you want to call this computer graphics or image processing. There's inputs in image and the outputs in image if you want, but there's also a geometry involved. That's that height field. So in some sense, it's a kind of image processing that gives us interesting effects. And you might actually find a good use for it. So if a pixel is supposed to represent an image, maybe what we have here is a representation of energy, and this form of energy we call it light. That's how I like to call it. So when I think about light, I think about an electromagnetic energy form that's visible, right? So illuminated electromagnetic energy is illuminated because the eye can perceive it. So it's meant for the human visual system when we start to talk about light. And so if the pixel is for humans, I'd like to know what the dynamic range of the eye is. And now it's looking like the eye can see 1 part in a million. That's a remarkable thing. That's a very sensitive thing. And what does that mean, to see 1 part in a million? What it means is that I need, well, perhaps 20 bits worth of dynamic range in order to be able to differentiate colors. And so that 2 colors that are adjacent to one another that are different by up to 20 bits worth of difference can be seen by the eye. So if I take 2 colors, let's say I hold up red and then I hold up another form of red, you'll look at it and you'll say, oh, they both look like red. But if I hold the 2 reds together, you'll say, oh no, they don't look the same. Because your ability to differentiate that those 2 different colors is accurate to within 1 part in a million. So that's really remarkable, and that's interesting, and what that means is to achieve a smooth transition between one color and the next on your screen without seeing artifacts, I need 1 part in a million. Not only that, but it's also true for the audio system. If I want to take a digital oscillator and change its frequency smoothly, I am endeavoring to create an effect which in music they call glissando. And that smooth change in frequency can only happen without perceptual notice of the difference in frequency. That is, that a change so gradual you can't hear the individual changes can only happen if you have 1 part in a million. So it's a synesthetic, which means it's a cross-perceptual phenomenon. Synesthesia refers to things that affect multiple senses at the same time. So, for example, you can see something with your eyes, and you can also hear what's going on, and together they make something that's the sum of the parts is greater than the individual components. So this is how you pack a pixel. 24 bits worth of color. This is assuming you're quantizing everything with integers. This is typical. They call this a direct color image. And this is giving you 24 bits worth of color for red, green, and blue, and then an overlay plane, which is often called alpha, the alpha plane. And here's your basic image sensor. And it's a phenomenon which is arrived to us because of microelectronic packaging. It's a charge-coupled device, or CCD. And what this is a chip with a glass top that has been assembled in a clean room. And what you do is you get a lens, and you focus the light onto the CCD array. And if you were building a camera, you would call it the film plane. Only the film plane, in this case, is not 35 millimeters like it is with standard film. It's more like 5.5 millimeters, or in certain cases where there are very large CCDs, it can be bigger. And so when you have that kind of a film plane, you have to change the focal length of the camera. The focal length refers to the distance between the aperture and the actual receiver of the light. So what you're looking for in a normal lens with a 35 millimeter film plane is a 55 millimeter focal length, which means that the lens is 55 millimeters away from the film plane. Whereas if you are dealing with a 4.5 millimeter film plane, CCD array, you probably don't want a focal length of much more than perhaps 12 millimeters, maybe less. So you look at the mounts for the cameras that go for CCD cameras, and they are completely different and use totally different lenses than the mounts you use for your film cameras. Right? They're meant for different size film planes. They're meant for a different offset. Pixel size. That's so key. Once the pixels get very small, they need a lot more light. They become less sensitive. That's an engineering trade-off. So when you go to these very high resolution chips, if the pixels are getting very small, you need more light. Otherwise, you need a bigger array, which means a much more expensive chip. So here's the resolution of the camera chip. How does that compare with the resolution of film? Right? Film has resolution, right? Has grain. You can only perceive certain things with certain size, right? How many, let's say, pixels does a 35 millimeter slide have? Any idea? Well, there are two kinds of film. There's the dog breath garden variety supermarket film. That's 100 lines per millimeter. And then there's the high-end laboratory-grade holographic film. That's 1,000 lines per millimeter. That's like a micron. So if you're thinking in terms of film and its resolution, if you have 35 millimeter film, and you take that 35 millimeter and multiply it by 100 lines per millimeter, right, and you're looking at 3,500 pixels on a side. And if you take that and you square it, 35 times 35 is 1225, and add another 4 zeros to that, that's how many pixels you got, whatever that comes to. So film is still king in terms of resolution. Is anybody computing that? No?
I did 3500 if I grew right.
It's 1225.
Yeah.
Oh yeah, I was right. How about that? I was going to get the calculator and just do it. So I have 35 times 35, and I said it was 1225. And that's right. And then it was times 100 lines per millimeter, so it would be 3,500 times 3,500, which comes to, that's a big number. What is that, like 12 megs? Let's see. Yeah, 12 and a quarter megapixels in dog breath supermarket film. 12 megapixels. Now, are cameras 12 megapixels? Maybe some.
They go more.
They go more? Yeah?
I was 16 megapixel, just digital camera.
And that's not a particularly remarkable camera. It's just a point and shoot. So film is not king anymore. Now digital cameras are king. Well, that's pretty cool. 16 megapixels is common?
It wasn't like an expensive camera. Yeah, you know what's interesting is a lot of those like high megapixel cameras end up being not as good as some lesser megapixel.
Well, it's also it's a function of the lens as well.
Light sensor too.
Yeah, if your lens is poor, you won't do well. Sometimes what people do is they make plastic injection molded aspheric lenses. And if you're doing stuff like that, I don't know how good it can be. But the electronics is able to do it.
Are there any other factors you know about that would make a high megapixel camera bad?
Size of the sensors. Remember, if you increase the pixel density, you need more light. So what you want to do is you want a larger film plane or a larger CCD array with a slightly lower density. That makes it much more sensitive to light. So sometimes they bill it as a 1/3 inch sensor or a 1/2 inch sensor. Hasselblad probably has a large format sensor. Don't know what it would be. So getting those larger sensors will make the camera more sensitive. So there's two kinds of color systems that we know about for human visuals display. One is called the additive synthesis system, and the other is called the subtractive synthesis system. With the additive synthesis system, the color primaries are red, green, and blue. With the subtractive synthesis system, the color primaries are cyan, yellow, magenta, and black. With cyan, yellow, and magenta, you can create black if you use them in equal quantities. But what people do is they take the equal quantities of cyan, yellow, and magenta, and they remove them to the black color plane, doing what's called gray component removal. This saves on the more expensive color inks. Moreover, if you want to create black text with a clear outline, if you use red, green, and blue, and they're slightly offset, things will look blurry. But you can get crisp black text if you have a black color plane. So when you go to get an inkjet printer, really what you want is to make sure that you have a lot more black in the ink cartridges than you have the other colors, because you'll be using black more. So when you see these black ink cartridges, they're generally oversized relative to the cyan, yellow, and magenta. For the additive synthesis systems, like this display projector, you add equal quantities of red, green, and blue, and you get white. You don't get black. And what you want to do to make black letters happen, like you can see in this display, is you remove the red, green, and blue. So we talked about image sampling. We talked about spatial resolution. What about pixel density? Pixel density can be described not just for the sensor, like for example your scanner or for your CCD array element, but also for the display. So when you talk about the display, when the Mac first came out, it was a Mac Plus, I think, or the Mac XE. That was 72 pixels per inch. Pixels are different from dots. Right? Pixels are different from dots. If you go to an inkjet printer is rated in dots per inch, not pixels per inch. Why? Well, because what the inkjet printer does is it squirts ink in dots. That's all it can do. So if you have, I don't know, call it 2,500 dots per inch, what you're doing is you're going to take those dots and you're going to organize them in order to create pixels. So what you do is you paint rosettes, where each one of the rosettes consists of cyan, yellow, and magenta arrays, and the arrays are dither matrices. And the dither matrices are used in order to be able to approximate a pixel. And your eye looks at those individual dots, and then it proceeds to integrate them into pixels. So if you take a magnifying glass and you look at the color images on the cover of my book or on the tip-ins, what you will see is you will see individual rosettes, because that's part of the color separation printing process that occurs inside of a normal printing press. Because normally what happens is they print the cyan, yellow, magenta, and black planes separately, and then they image plates using film. And the film is able to make a very good black, a very high density opaque black, and then you illuminate the plates with ultraviolet light, and that allows them to be developed so that when you go and put ink onto the plates, it adheres into the crevasses that are created during the development process, and then you can print them straight onto paper. So part of the printing process requires that we use dots, and so we think in terms of dots per inch. This is a little too much animation here. I'm going a little too fast. I don't like this swishing sound. I think I put in too much fanciness. Okay, so the point of this slide is to show that if you have an insufficient spatial resolution, you can get sampling error. Here, where we're sampling slightly off from the left from the right, we can see we get output images which are slightly different. We get artifacts in the resampling of the input images. So how do I know what the quantization density should be, right? What spatial resolution should I use? And that goes to the question of Nyquist again. Nyquist had to do with frequency, but it also works for images. And so what we could say is, if I know what the spatial resolution is of the image, that is the highest frequency thing that I want to try and resample, then I can determine what my spatial resolution should be for my input sensor. So if what you're trying to measure is something like a tumor, and the tumor is, let's say, 10 millimeters, well then you'd better have something that can resolve down to at least 5 millimeters. Otherwise you could miss the tumor. And you probably want to go even better. Oh, more sound effects. Okay. So here's the Nyquist rate. That's really annoying. I'm going to put a stop to this right now. There we go. Enough of that. So here, if we double our sampling rate... Oh, really? I have to start again? Stop it. Hey, how do you turn off these effects? There has to be a way. So,
Mute the computer.
Huh?
Mute the computer.
Mute the computer.
Turn the volume down, you won't hear it.
Ooh. What a high-tech way to go. I could probably plug something into the headphone jack, and then we wouldn't have to hear it. That's good, too. Mute the computer, he says. Oh, you must be one of those computer engineers. Is there a function key for that? No? Can't be bothered. I'll figure that out later. Now, I'll figure it out during the break. Actually, it's already, I fast-forwarded through it, so there you go. So now we have practical examples of downsampling an image. Resampling, as it's sometimes called, allows us to change the resolution of the image. Once you do that, the process is said to be irreversible. But is that really true? Is it possible for me to go back from here to there without looking at the original image? You know, one of the things I noticed is that if you look at CSI, they point at some surveillance video and they say, zoom in on this. And the guy says, okay, and then somehow magically the resolution improves when you zoom in. Somebody should tell people zooming in doesn't make more pixels. It just doesn't work that way. Zooming in doesn't make it clearer. Oh, zoom in on that, and then all of a sudden you can see their reflection in the mirror. I know who that is. And you're like, well, wait, the mirror was like a side view mirror in a car, and you're looking at somebody through this side view mirror that's 2 pixels, and you're zooming in, and now you can see their face. No, I'm sorry, that doesn't work that way. And CSI is great because
The show wouldn't be very fun without.
yeah, they do stuff they'll do, oh, we'll have to sequence this genome, and they get it all done by the commercial break. That's the magic of television. It's kind of like when Julia Child says, oh, let's put this in the oven, and by the way, and this is what it looks like when it's done. But what she doesn't say is, hey, it took 3 hours to cook it. So one of the things that I like to do is I like to use packed pixels. And packed pixels enables us to essentially be very efficient with how we use our data. So if I can take the little red pixel and put it in the least significant 8 bits, and then take the little green pixel and put it in the next least significant 8 bits, and then take the blue pixel and put that into the least significant, the next least significant 8 bits, which would be, bits 0 through 8 versus 9 through 16 versus 17 through 24. To do that, I need to know about bitwise operations. And so what that requires me to do is to take data and shift it and then mask it into our ints. So the int quantities can be packed properly, but we need to know how to do bitwise operations. And while we might understand them because we had digital design, we might not necessarily know how to do these things as programmers. So bitwise operations as programmers are done with operations which are kind of like the logical operations we know about from programming, with a difference. And the difference is they look a little bit different. So when you take a Boolean operation, in Java, and there are 2 Boolean variables that could have value of true and false, you use ampersand, right? So if you said if A and B, are true, then you use ampersand, ampersand. But if what you're trying to do is a bitwise AND, you use a single AND percent. And the bitwise AND allows you to take the ones and zeros inside of a value and AND them together directly. So you may or may not have done that before. Has anyone here tried that before? No? It's kind of a Java lesson. But if you want to, we'll go through a couple of examples. So there are a couple of ways in which you can do OR. Right? In Boolean algebra, you've heard of the inclusive OR. Right? Inclusive OR says if any of the bits is 1, then the output is 1. If both of the inputs are 0, then the output is 0. Exclusive OR is different. Right? With exclusive OR, if both of the inputs are 1, the output is 0. If one is 1 and the other is 0, the output's a 1. If one is 0 and the other is 1, the output's a 1. If both the inputs are 0, the output's 0. So you know about exclusive OR. Well, exclusive OR in Java is done with a little caret. That's the XOR. How do I get the... Oh, there it is. See that little thing? If you take the little caret that goes up in the air, and you put that between X and Y, then that makes a bitwise exclusive OR operation. If you use the exclamation point, that means you're dealing with a Boolean variable whose value could be true or false. But if you use the tilde, that's an inverse operation that is bitwise. So Boolean operations and bitwise operations are really different in Java. They use different operators, they have totally different effect, and they expect different arguments. They're binary operators that take two arguments, take two inputs. Binary operators, when you refer to a programming language, a binary operator is an operator that takes an argument on the left-hand side of the operator and an argument on the right-hand side of the operator. So, for example, times is a binary operator because it takes two arguments. It's not binary in the digital design sense where the inputs are ones and zeros. Other operators are what they call unary operators. In programming languages, when we talk about an unary operator, it takes only a single argument. So, for example, bang, the exclamation point, is an unary operator. Tilde, the bitwise inversion, is an unary operator. But exclusive OR is a binary operator that takes an argument on the left and an argument on the right-hand side. I'm thinking it's probably a good time for a break. What do you think?